Hi, welcome to the ComSci 137 lecture. Sunny here. For this module, we will be discussing wireless LAN. Let's start. Wireless communication is one of the fastest growing technologies. The demand for connecting devices without the use of cables is increasing everywhere. Let us first compare the architecture of wired and wireless LANs. The first difference we can see between a wired and wireless LAN is the medium. In a wired LAN, we use wires to connect hosts. In a wireless LAN, the medium is air. The signal is generally broadcast. In terms of hosts, in a wired LAN, a host is always connected to its network at a point with a fixed link layer address related to its network interface card. Of course, a host can move from one point in the internet to another point. In this case, its link layer address remains the same, but its network layer address will change. In a wireless LAN, a host is not physically connected to the network. It can move freely and can use the services provided by the network. The concept of a wired isolated LAN also differs from that of a wireless isolated LAN. A wired isolated LAN is a set of hosts connected via a link layer switch. A wireless isolated LAN, called an ad hoc network in wireless LAN terminology, is a set of hosts that communicate freely with each other. The concept of a link layer switch does not exist in wireless LANs. There are several characteristics of wireless LANs that either do not apply to wired LANs or the existence of which is negligible and can be ignored. First is attenuation. The strength of electromagnetic signals decreases rapidly because the signal disperses in all directions. Only a small portion of it reaches the receiver. The situation becomes worse with mobile senders that operate on batteries and normally have small power supplies. Next is interference. Another issue is that the receiver may receive signals not only from the intended sender, but also from other senders if they are using the same frequency band. Another is multifat. A receiver may receive more than one signal from the same sender because electromagnetic waves can be reflected back from obstacles, such as walls, the grounds, or objects. The result is that the receiver receives some signals at different phases. This makes the signal less recognizable. With all the characteristics of a wireless network mentioned, we can expect that errors and error detection are more serious issues in a wireless LAN than in a wired LAN. If we think about the error level as the measurement of signal-to-noise ratio, we can better understand why error detection and error correction and retransmission are more important in a wireless network. IEEE has defined the specifications for a wireless LAN, called IEEE 802.11, which covers the physical and data link layers. It is sometimes called wireless Ethernet. In some countries, the public use the term Wi-Fi, short for wireless fidelity, as a synonym for wireless LAN. Wi-Fi, however, is a wireless LAN that is certified by the Wi-Fi Alliance, a global, non-profit industry association of more than 300 member companies devoted to promoting the growth of wireless LANs. The standard defines two kinds of services, the basic service set and the extended service set. IEEE 802.11 defines the basic service set as the building blocks of a wireless LAN. Basic service set is made up of stationary or mobile wireless stations and an optional central base station known as an access point. The BSS without an AP is a standalone network and cannot send data to other BSS. It is called an ad hoc architecture. In this architecture, stations can form a network without the need of an AP. They can locate on one another and agree to be part of a BSS. A BSS with an AP is sometimes referred to as an infrastructure BSS. An extended service set is made up of two or more BSS with APs. In this case, the BSS are connected through a distribution system, which is a wired or wireless network. The distribution system connects the APs in the BSS. IEEE 802.11 does not restrict the distribution system. It can be any IEEE LAN, such as an Ethernet. Note that the extended service set uses two types of stations, mobile and stationary. The mobile stations are normal stations inside the BSS. The stationary stations are AP stations that are part of a wired LAN. IEEE 802.11 defines three types of stations based on their mobility in a wireless LAN: no transition, BSS transition, and ESS transition mobility. A station with no transition mobility is either stationary or moving only inside a BSS. A station with BSS transition mobility can move from one BSS to another, but the movement is confined inside one ESS. A station with ESS transition mobility can move from one ESS to another. However, IEEE 802.11 does not guarantee that communication is continuous during the move. IEEE 802.11 defines two MAC sublayers, the distributed coordination function and point coordination function. This figure shows the relationship between the two MAC sublayers, the LCC sublayer and the physical layer. One of the two protocols defined is the distributed coordination function, or DCF. DCF uses CSMA/CA as the access method. It cannot use CSMA/CD because stations must send and receive at the same time, which is costly. The collision may not be detected because of the hidden station problem, and the distance between stations may be great. Here is the flowchart of the CSMA/CA in wireless LANs. Before sending a frame, the source station senses the medium by checking the energy level at the carrier frequency. The channel uses a persistent strategy with backoff until the channel is idle. After the station is found to be idle, the station waits for a period of time called the distributed interframe space, or DIFS. Then the station sends a control frame called the request to send, RTS. After receiving the RTS and waiting a period of time called the short interframe space, or CIFS, the destination station sends a control frame called the clear to send, or CTS, to the source station. This control frame indicates that the destination station is ready to receive data. The source station sends data after waiting an amount of time equal to CIFS. The destination station, after waiting an amount of time equal to CIFS, sends an acknowledgement to show that the frame has been received. Acknowledgement is needed in this protocol because the station does not have any means to check for the successful arrival of its data at the destination. How do other stations defer sending their data if one station acquires access? In other words, how is the collision avoidance aspect of this protocol accomplished? The key is a feature called nav. When a station sends an RTS frame, it includes the duration of time that it needs to occupy the channel. The stations that are affected by this transmission create a timer called a network allocation vector, or nav, that shows how much time must pass before these stations are allowed to check the channel for idleness. Each time a station accesses the system and sends an RTS frame, other stations start their nav. What happens if there is a collision during the time when RTS or CTS control frames are in transition, often called the handshaking period? Two or more stations may try to send RTS frames at the same time. These control frames may collide. However, because there is no mechanism for collision detection, the sender assumes there has been a collision if it has not received a CTS frame from the receiver. The backoff strategy is employed and the sender tries again. Here is the diagram for CSMA/CA and nav. The point coordination function, or PCF, is an optional access method that can be implemented in an infrastructure network. It is implemented on top of the DCF and is used mostly for time-sensitive transmission. PCF has a centralized contention-free polling access method. The AP performs polling for stations that are capable of being polled. The stations are polled one after another, sending any data they have to the AP. To give priority to PCF over DCF, another interframe space, PIFs, has been defined. PIFs, or PCF IFS, is shorter than DIFs. This means that if at the same time a station wants to use only DCF and an AP wants to use PCF, the AP has priority. Due to the priority of PCF over DCF, stations that uses only DCF may not gain access to the medium. To prevent this, a repetition interval has been designed to cover both contention-free PCF and contention-based DCF. The repetition interval, which is repeated continuously, starts with a special control frame called the beacon frame. When the station hears the beacon frame, they start their nav for the duration of the contention-free period of the repetition interval. During the repetition interval, the PC or point controller can send a poll frame, receive data, send an acknowledgement, receive an acknowledgement, or do any combination of these. At the end of the contention-free period, the PC sends a contention-free end frame to allow the contention-based stations to use the medium. The wireless environment is very noisy, so frames are often corrupted. A corrupt frame has to be retransmitted. The protocol therefore recommends fragmentation, the division of a large frame into smaller ones. It is more efficient to resend a small frame than a large one. The MAC layer frame consists of 9 fields as shown here. The frame control field is 2 bytes long and defines the type of frames and some control information. The table shows the subfield values of the frame control field. The D field defines the duration of the transmission that is used to set the value of nav. In one control frame, it defines the ID of the frame. There are 4 addresses fields, each 6 bytes long. The meaning of each address field depends on the value of the 2DS and from DS subfields. The sequence control field, often called the SC field, defines the 16-bit value. The first 4 bits define the fragment number, the last 12 bits define the sequence number, which is the same in all fragments. The frame body field, which can be between 0 and 2312 bytes, contains information based on the type and subtype of defined in the FC field. FCS field is 4 bytes long and contains a CRC32 error detection sequence. A wireless LAN defined by IEEE 802.11 has 3 categories of frames: management frame, control frames, and data frames. Management frames are used for the initial communication between stations and access points. Data frames are used for carrying data and control information. Control frames are used for accessing the channel and acknowledging frames. For control frames, the value of the type field is 01. The values of the subtype fields for frames we have discussed are shown in the table. The IEEE 802.11 addressing mechanism specifies 4 cases, defined by the values of the 2 flags in the FC field, 2DS and from DS. Each flag can either be 0 or 1, resulting in 4 different situations. The interpretation of the 4 addresses in the MAC frame depends on the values of these flags, as shown in the table. Note that address 1 is always the address of the next device that the frame will visit. Address 2 is always the address of the previous device that the frame has left. Address 3 is the address of the final destination if it is not defined by address 1, or the original source station if it is not defined by address 2. Address 4 is the original source when the distribution system is also wireless. The hidden station problem can reduce the capacity of the network because of the collision. This can be explained using the figure. Here, stations B and C are not in each other's range, but both are in the range of station A. Since B and C are hidden from each other, they may send data to A at the same time, which cause a collision. The solution to the hidden station problem is the use of handshake frames. Here shows the RTS message from B reaches A, but not C. However, because both B and C are within the range of A, the CTS message, which contains the duration of data transmission from B to A, reaches C. Station C knows that some hidden station is using the channel and refrains from transmitting until the duration is over. A similar problem is called the exposed station problem. This problem, a station refrains from using a channel when it is in fact available. Here, Station A is transmitting to Station B. Station C has some data to send to Station D, which can be sent without interfering with the transmission from A to B. However, Station C is exposed to transmission from A. It hears what A is sending and thus refrains from sending. In other words, C is too conservative and wastes the capacity of the channel. The handshaking messages RTS and CTS cannot help in this case. Station C hears the RTS from A and refrains from sending even though the communication between C and D cannot cause a collision in the zone between A and C. Station C cannot know that Station A's transmission does not affect the zone between C and D. Here are the evolution of the specification of the IEEE 802.11. All implementations, except the infrared, operate in the ISM band. The ISM band is the internationally reserved portion of the radio frequency bands for industrial, scientific, and medical uses. It does not need for government licenses. It was opened up for wireless LANs and mobile communications. IEEE 802.11 FHSS uses the frequency hopping spread spectrum method. The band is divided into 79 subbands of 1 MHz. A pseudo-random generator selects the hopping sequence. The IEEE 802.11 DSSS uses the direct sequence spread spectrum method. DSSS uses the 2.4 to 4.835 GHz ISM band. The modulation technique in this specification is PSK at 1 mbaud per second. IEEE 802.11 infrared uses infrared light in the range of 800 to 950 nanometer. Modulation technique is called pulse position modulation. The map sequences are converted to optical signals. The presence of light specifies 1, the absence of light specifies 0. IEEE 802.11a OFDM describes the orthogonal frequency division multiplexing method for signal generation in a 5.725 to 5.85 GHz ISM band. OFDM is similar to FDM with one major difference. All the subbands are used by one source at a given time. Sources contend with one another at the data link layer for access. The band is divided into 52 subbands with 48 subbands for sending 48 groups of bits at a time, and 4 subbands for control information. Dividing the band into subbands diminishes the effect of interference. If the subbands are used randomly, security can also be increased. OFDM uses a PSK and QAM for modulation. The common data rates are 18 Mbps for PSK and 54 Mbps for QAM. IEEE 802.11b DSSS describes the high-rate direct sequence spread spectrum method for signal generation in the 2.4 4.835 GHz ISM band. HRDSSS is similar to DSSS except for the encoding method, which is called the complementary code keying or CCK. CCK encodes 4 or 8 bits to one CCK symbol. To be backward compatible with DSSS, HRDSSS defines 4 data rates: 1, 2, 5.5, and 11 Mbps. The IEEE 802.11g specification defines forward error correction and OFDM using the 2.4 to 4.835 GHz ISM band. The modulation technique achieves a 22 or 54 megabits per second data rate. It is backward compatible with 802.11b, but the modulation technique is OFDM. An upgrade to the 802.11 project is called the 802.11n, or next generation of wireless LAN. The goal is to increase the throughput of 802.11 wireless LANs. The new standard emphasizes not only the higher bitrate, but also eliminating some unnecessary overhead. The standard uses what is called MIMO, or multiple input, multiple output antenna, to overcome the noise problem in wireless LANs. The idea is that if we can send multiple output signals and receive multiple input signals, we are in a better position to eliminate noise. Some implementations of this project have reached up to 600 Mbps data rate. It is now labeled as Wi-Fi 4. The latest standard today is the 802.11ac, relabeled as Wi-Fi 5, has a frequency band of 5.8 GHz ISM band and a max data rate of 6.93 gigabits per second. It implements the multi-user MIMO, which enables simultaneous transmission of different data frames to different clients. 802.11ax, relabeled as Wi-Fi 6, has frequency bands 2.4 GHz and 5 GHz. 6 GHz is used for Wi-Fi 6E. It uses a multi-user technology, the OFDMA, and the multi-user MIMO. The max data rate for a 80 MHz channel is 600.4 megabits per second and 9 gigabits for a 160 MHz channel. This ends part 1 of Module 17. Thank you.